Good day. We are going to build on the previous PowerPoint and get to more complicated equilibrium calculations. We're going to start off with a type of question you saw in the previous PowerPoint, but then we're going to get more exotic. We're going to start in situations that aren't equilibrium, and we're going to move to equilibrium, and that means we will be doing ice charts. So earlier you learned about KEQ expressions, and from that you should be able to solve for KQ or an unknown concentration. And eventually in this PowerPoint we're going to look at ice charts where we have changing conditions. So we love questions that already involve being at equilibrium because then we don't have to do an ice chart. So here we're told we have this equation. So solid carbon gets together with hydrogen to make methane. And we're given a KQ value. We're given the concentration of CH4 at equilibrium. And we're asked to find the hydrogen concentration. We can ignore the carbon because it's a solid. It won't be part of the KQ expression. So this is a good general rule. Start by writing out the KQ expression, and there it is, products over reactants. What we do is we rearrange this equation to solve for the unknown. The unknown was hydrogen. So the hydrogen squared goes up here and the KQ comes down here, moving diagonally across the equal sign. And we punch in the numbers from the question, boom divided by boom, and we have to understand that that is squared, but we just want the hydrogen concentration, so we're going to take the square root. And let me practice making my square root symbols. So then we're going to go square root of that is the square root of that, and we arrive at that answer, 1.6 times 10 to the minus 5m. So hopefully that's straightforward. Now this question is a little more interesting because we're given what we have at the start. It says we have 2 moles of HI, and it happens to be a 1 liter flask. And when we use ice, we like to use concentrations. So this will just become 2.00 big M. And we are assuming that we have no hydrogen or iodine at the start. So we have to get the equilibrium, and that means Le Chatelier says this equilibrium is going to the right. And we're going to use up some of the HI, so it's going to drop, and we're going to make some hydrogen and iodine. In fact, it tells us how much we made. So this turns out to be a fairly tidy question. And eventually, we're going to calculate the KQ. So we write out the equation, the chemical equation, remembering coefficients. Often we don't put in the states if they're all gases, but it's not a bad idea too. And down the left we go ICE, and this is why it's called ice chart. Initial change equilibrium. Well, initially I believe we were told it's 2.00 m, and we were also told the concentration of hydrogen and iodine at equilibrium. So there we are. We start with none of those guys, and this is not the order I would have done it, but this is my crazy PowerPoint. So let's just show you how we really would have done it. First things I would have written in are this, 2.00 m, and I would have written in these 2 numbers right here. That's what I'm getting from the question. Well, we have coefficients of 2 and 1 and 1. So this went up by 0.214, and this went up by 0.214. Remembering Stoich from last year, we have to react twice as much of this to make that. So we take this number and we double it, and we get minus 0.428. So eventually we're going to have situations where we're not told these things, and we'd have to use this algebra. We really don't have to use the algebra. So we go 2.00 minus 0.428 big M, and we arrive at our final concentration of HI. Now we have all the information that we need to get the KQ value because we have the equilibrium concentrations. Remember sig figs. So we write out the KQ expression for the reaction. We plug in the numbers from the previous page. We had the 0.214 times 0.214, and we have 1.57 all squared. And then we trust our calculator to belch out the right answer. And remember sig figs. And when we write out KQ values, typically we don't include units. The textbook, for some reason, loves to put in units. I would not bother. Do not put in units. So that's the answer to that question. Let's see how we're chugging away here. Well, we have a friendly reaction here. And we are told we have these initial concentrations. We have this equilibrium. And we are given the hydrogen concentration at the end. So in fact, we're going to have all the information we need to avoid any serious algebra. We're going to write this equation out. We're going to write ice. And we're going to plug in numbers. You hear some horrendous noises. It's a dog chewing its nail off. Very unpleasant. So there's the equation. There's our ice. And we start rolling in the numbers. Those were given in the question. And you say, how do we know these things? Well, the question basically gave us this, and this, and this. And what we saw was, going 0.66 minus 0.30, we could get our change. Now this amount will be x, this will be 3x, and this will be 2x. And that's from the coefficients, the 1, the 3, and the 2. So there's a minus 0.36, minus 0.12. And we know it's minus on this side because we had no product, it had to go on the right, and it's plus on this side. So we end up with a 0.24, we have the 0.30, and we do a subtraction, we get 0.20. Now we're going to write out the KQ expression, and we're going to use these values because it's equilibrium. So that's it. Now we substitute in our numbers, and we let the calculator belch out an answer, and it comes up with 11. We're going to stop here, and we'll carry on in the next video to complete the PowerPoint.